For today's notes, we are taking a look at a specific type of AP problem that shows up often on the free response section of the AP exam. Notice the problem. This problem can be found. It's in your AP Review 4.5 packet. It's question number 2 in the free response part. But notice this problem and lots that are on the AP exam. You are given the rate at which something is added. So in this case, we've got a ski resort. They're using a snow machine to control how much snow is on the ski slope. And then it tells us that the amount of snow added per hour is given by this equation. So this is the rate at which we're adding snow, and then this is the rate at which snow is melting. We're always given a rate added and or a rate removed. Usually both are given. Sometimes I've seen a couple of them where it's just one. So rate added, rate removed. These are both rates of change. It tells us that both S of t and M of t have units of cubic yards per hour. T is measured in hours from 0 to 24. This is a calculator problem. Almost always this is on the calculator part. Notice also it gives us an initial condition. It tells us at time 0, we have 50 cubic yards of snow. Part A wants the total volume of snow added to the mountain over the first 6-hour period. So we are only looking at how much snow has been added. This is a rate of change. To go from a rate of change to a total amount, we need to integrate. We are only integrating S of t because we only care about how much snow has been added to the ski slope. We want over the first 6-hour period, so time starts at time 0 and ends at time 6. Because this is a calculator problem, we can then go to y equals on our calculator. Type in our equation, 24 minus x times sine squared of x over 14. So sine of x over 14 squared. We should change our window to go from 0 to 24 because we're looking at the first 24 hours. The y min and max, let's leave it negative 10 to 10 for now. And take a look at our graph. It looks like most of our graphs up here somewhere. You can either just kind of guess and check until you have a good graph, or if we look at our table, looking at the table, it looks like it starts at 24 and just goes down from there. So my y max, I'm going to make 24. Pushing graph, we now have a pretty good graph of S of t. And we can integrate S of t, second trace. Number 7, the integral of f of x dx, starting at time 0, enter, and ending at time 6. And we find that those first 6 hours we have added 142.413 cubic yards of snow. This is all the work that would be required to earn full credit for Part A. Part B asks us to find the first time that the instantaneous rate of change of the volume of snow is 0. The first time the instantaneous rate of change of the volume of snow is 0. So we want the overall rate of change to be 0. So this is the rate at which snow is added as S of t. And then we want to take away the rate at which snow is melting. And we want that overall rate to be 0. So rate added minus rate removed, overall rate should be 0. On our calculator, later we're probably going to need S of t, so we don't want to change y1. Let's go down to y2 and type in m of t. 10 plus 8 cosine of x over 3. You should probably double check, make sure in radians mode also. And then I want to take S of t minus m of t. S of t is y1, m of t is y2. So we can type in y1 and y2 by pushing alpha trace. y1 minus y2. If we graph right now, it's going to graph all three of these. We only want to work with y3. So let's turn off graphs 1 and 2. y1 and y2 we can turn off and take a look at what our graph looks like. We're looking for the first time that it is equal to 0. It's actually only equal to 0 once over those 24 hours. Calculate the 0. It's somewhere between 10 and 20. I changed my scale to 10. Left bound 10, right bound 20. Guess, just push enter. And my time is 15.040 hours. Part C. Part C wants to know, is the volume of snow increasing or decreasing at time 4? The overall volume of snow increasing or decreasing at time 4. So we want to compare the rate at which we are adding snow and the rate at which snow is melting at time 4. A couple different ways you could do it. The first is we could find S of 4 and M of 4 and just compare them. Whichever one's bigger would tell you which one, or if we are adding or melting more snow. So S of 4 and M of 4, you can get either by plugging them into the equation, or if we look at our table. Second graph, right now it's just showing y3 because we turned off our other graphs. Turn y1 and y2 back on. At time 4, y1 is 23.682. If you ever need more decimals than it shows, you can highlight it and it shows the whole thing down here. 23.682. M of 4 is 11.882. We are adding snow at a greater rate than it is melting. So we have an increasing amount of snow. A lot of times it tells you to justify your answer. Show this, state increasing, and then you can simply say S of 4 is greater than M of 4. The other way you could do it is to take a look at the overall rate of change. The overall rate of change is S of 4 minus M of 4. And then you're checking to see, is the overall rate of change positive or negative? So you would be looking at y3 here is 11.800. And then you would say increasing because S of 4 minus M of 4 is positive. Part D, we are going to change what it says on your paper there. Part D, let's suppose it asks, it's a very common problem. It asks how much snow is on the slope, or what is the volume of snow on the slope at a specific time at t equals 10. So how much snow is on the slope at time 10? So now we need to take into account how much snow we've added, starting at time 0 and ending at time 10. We also need to take into account how much snow has melted from 0 to 10. And we also need to consider that we started with 50 cubic yards of snow. So to do this, again, we're going from our rate of change to an amount. So we are going to integrate, starting at 0, because that's when we know how much snow there is, and ending at time 10, because that's the time at which we are looking for how much snow we have. And we want to integrate S of t minus M of t, the overall rate of change. Take how much snow's added, subtract the amount of snow that's melted. Don't forget your dt. That is going to tell us how much the amount of snow on the ski slope changes by ski slope. We also need to consider that it started with 50 cubic yards. We can just add that at the end here. So we are graphing S of t minus M of t. That is my Y3 graph. Turn the first two off. We need to integrate. Second trace, number 7. Starting at time 0 and ending at time 10. So during those 10 hours, we have added 133.193 cubic yards of snow, plus the 50 we started with, gives us a total amount of snow of 183.193 cubic yards. So again, a pretty common type of problem there. We are going to take a look at a second one that we'll work through together here. This is one that was actually on the AP exam. So the problem we're doing is the 2002 problem, question number 2. I will post a copy of it in Google Classroom so you can access it there instead of trying to jot it down. But similar setup here. Notice, again, we're given rates of change. Rate. This is the rate at which people are entering an amusement park, rate added. And we are also given the rate of change that people are leaving the same amusement park. Very typical problem. 2 equations, one for rate added, one for rate removed. We're also given an initial condition. At time 9, we know that there's nobody in the park. Just like they told us on the last problem, at time 0, we knew how much snow there was in the park. Part A wants to know how many people have entered the park by 5 p.m. So we are just looking at the people that have entered the park. So we are integrating E of t dt. Only E of t because it's just the people entering. We are integrating because we were given a rate of change and we're trying to get to a total number of people. We want to start at time 9. At time 9 is when the park opens, and end at time 17, which is 5 p.m. So go ahead, type your equations into your calculator, integrate, and see what you get there. I'm going to turn my Y3 graph off. We'll probably need it again. I'm going to go ahead and type in L of t under Y2. We only are integrating Y1, so Y2 graph should be turned off. And we are integrating starting at time 9 and ending at time 17. Notice we can't see the curve. It's way up there somewhere. You can play with the window until you get it. You actually, as long as your graph is within the domain, within the x's, it doesn't actually have to be within the range. So we can integrate from 9 to 17, and it's going to find the area under the curve all the way up to the curve, no matter how high it is. It does tell us, and it does this occasionally, round your answer to the nearest whole number, which makes sense. We're talking about people here. You can't have 0.270 people. So 6,004 people. Part B says the price of admission to the park is $15 until 5 o'clock. And then after 5 p.m., the price of admission is $11. How many dollars are collected from admissions to the park on a given day? So we know that we had 6,004 people that came into the park over those first, 8 hours from t equals 9 to t equals 17. So those 6,004 people are paying $15 a piece. We need to figure out how many people enter the park from 5 p.m. until they close. Looks like they close at 2,300 hours at t equals 23. So we want to integrate from time 17 to time 23 of e of t dt. E of t is the graph that is currently up. So we are integrating from 17 to 23. And we find that 1,271 people, 1,271, pay that $11 to get into the park. And now it's just a little multiplication and addition. And we find that they bring in $104,041 in a given day. Part C. Part C says let h of t equal the integral from 9 to t of e of x minus L of x dx. It tells us the value of h of 17 is 3725. We need to find what h prime of 17 is and explain the meaning of both h of 17 and h prime of 17. So h of 17, we have an equation for h of x. So if I plug in 17 here, notice we would be integrating from 9 to 17 of e of x minus L of x dx. So we are taking the rate added minus the rate removed, and we are integrating it. So this is going to be the number of people in the park at t equals 17. And notice this is only true because there's nobody in the park at time 9. If there were people in the park at time 9, you could not state this. You would have to say it's the change in the number of people in the park at t equals 17, which would also be correct for part C here. So you can say the change in number of people in the park at t equals 17, or in this case, the total number of people in the park. So that is the meaning of h of 17. I probably should have stated that here. H of 17 represents the number of people in the park at t equals 17. Let's find what h prime of 17 is equal to. H prime of x would be the derivative of this. I'm sorry, h prime of t would be the derivative of this. To take the derivative of an integral, that's where we just plug in t for my x's. E of t minus L of t. So h prime of 17 is just e of 17 minus L of 17. So e minus L, that's my y3, y1 minus y2. I want to know what that is at time 17. You can get it by either finding the two values and subtracting them, or taking a look at your table at time 17. This is one of those cases. Notice that's not enough decimals. Highlight it. Negative 380.281. Negative 380.281. Explain the meaning of that. Notice this is the rate added minus the rate removed. So at t equals 17, the overall rate of change is negative 380.281 people per hour. The number of people in the park is decreasing by 380.281 people per hour at t=17. And then finally, part D, at what time does the model predict the number of people in the park to be a maximum? We need the number of people in the park to be a maximum. Remember, maximums and minimums occur when the derivative is 0, when the overall rate of change is 0. So number of people in the park, we said, was what this equation here is. That's the number of people in the park. I need the derivative of that to be 0. So I need E of t minus L of t to be equal to 0. We graph E of t minus L of t. Make sure we are looking at least from 9 to 23, which is all included on our graph here. E of t minus L of t is equal to 0 at that time right there. Let's calculate that 0. It's somewhere between 10 and 20. $15.795. That is our only critical number. Remember, maxes and mins don't have to occur at a critical number. They could also occur at the endpoints of the interval. So let's set up a little table here. Let's compare times with number of people in park. We need to make sure we have any critical numbers on there. The only one we know is 15.795. And we also need to check the endpoints, which is at time 9 and time 23. At time 9, there is nobody in the park. We were told that up here in the problem. At time 15.795, to figure out the number of people in the park, we are going to integrate starting at time 9 and ending at time 15.795. And usually we need to add our initial number of people. So we would add the initial amount, but remember the initial amount was 0. So we have 3,951 people in the park at that time. To check 23, we are going to integrate starting at 9 and ending at 23. Add the initial number of people, which is 0. Looks like one person's left when they close. So it makes sense that their ending time is not when they have the most number of people in the park, but this proves it. It just asks us to predict the time. We have proven that we have a maximum number of people at time 15.795.